Look at this split view of a bubbling soda and a bar of soap. If we zoom in to the microscopic liquid level, you can see bouncing H+ ions driving the fizz of the soda and OH- ions powering the cleaning action of the soap. Understanding how these specific, invisible ions behave is the foundational step to controlling industrial processes and mastering your O-level chemistry exams. In this flowchart of a water beaker, a hydrochloric acid molecule drops in and splits. The H+ ion earns a red label. Arrhenius acids release H+. Below, an NaOH molecule drops in and splits. The OH- ion gets a blue label. Arrhenius bases produce OH-. While this framework works for simple reactions, it relies on a substance explicitly releasing these ions in water, a requirement leaving some chemical behaviors unexplained. Take a look at this ammonia molecule. It acts exactly like a base, but looking closely at the chemical formula, we see no OH-. The Brønsted-Lowry theory resolves this by shifting focus to the act of donating or accepting protons. Watch as a water molecule appears next to the ammonia. An arrow pulls a single proton, H+, off the water and moves it to the ammonia. Water is the proton donor, acting as the acid, while ammonia is the proton acceptor, acting as the base. To map out conjugate acid-base pairs, you follow that single proton across the reaction. The bracket connecting NH3 on the left to the NH4+ product on the right tracks the addition of one proton. The second bracket connects the water to the OH- product, tracking the loss of one proton. Focusing on the movement of a single proton allows you to identify these relationships, even in reactions where water isn't involved. Beyond the microscopic level, this dashboard summarizes the observable physical properties of these reactions. You can see the pH scale sliding to red for sour-tasting acids or blue for bitter, slippery bases. And on the right, the reaction equation shows an acid reacting with a metal, releasing hydrogen gas bubbles. Let's test your intuition with this split-screen layout. Methane is on the left, and ethanol is on the right. Both formulas contain hydrogen or OH groups. Do they act as acids or bases? When both molecules drop into the water, you get a large red X. Both remain fully intact, failing to dissociate or release any H+ or OH- ions. Chemical behavior and actual proton movement dictate a substance's identity. Memorizing the letters in a written formula will lead you to the wrong conclusion. Even after mastering definitions, students frequently lose points on exams by conflating the strength of an acid with its concentration. This matrix breaks down the difference. The top row visualizes strength as a dissociation percentage. On the left, 10 out of 10 molecules split apart for 100% dissociation, indicating a strong acid. On the right, only 1 out of 10 splits apart, representing a 10% dissociation, or a weak acid. The bottom row illustrates concentration, which is purely the total volume of particles crammed into a specific space. The left beaker is highly concentrated with 50 intact molecules, while the right beaker has a low concentration of only 5 molecules. When we cross-reference the matrix, the distinction is clear. This highlighted beaker is densely packed with 50 molecules, giving it a high concentration, but almost none of them have split apart, meaning it has weak strength. Finally, capture this 3-panel dashboard as your study guide. Panel 1 contrasts the Arrhenius and Brønsted-Lowry definitions. Panel 2 groups the litmus properties and gas release rules. Panel 3 locks in the +or-1 proton rule for conjugate pairs. Combining these definitions, tracking proton movement, and distinguishing strength from concentration gives you the tools to handle the toughest questions on the paper.